Welcome! In this session, we'll be tackling an interesting problem from LeetCode, problem number 1277, count square submatrices with all ones. This problem challenges us to calculate the total number of square submatrices filled entirely with ones in a given binary matrix. We'll explore the solution step by step and analyze its complexity. Let's dive in. The problem asks us to count all square submatrices within a given binary matrix that consist entirely of ones. A binary matrix is simply a grid where each cell contains either a 0 or a 1. To clarify, a square submatrix means that the number of rows is equal to the number of columns, forming a perfect square. For instance, a 1x1 submatrix is a single cell, a 2x2 submatrix is a 2-row by 2-column grid, and so on. Our goal is to calculate the total number of these square submatrices where every element is a 1. The input is the binary matrix itself, which can have dimensions ranging from 1 by 1 up to 300 by 300. The output is a single integer, representing the count of all such valid square submatrices. Let's explore a few examples to understand this better. Consider the first example, where the matrix is a 3 by 3 grid. The output is 7, and here's why. First, each individual 1 in the matrix contributes a 1x1 square submatrix. Counting these gives us 6 single-cell squares. Then, there is one larger 2x2 square submatrix in the bottom left corner, formed by the group of ones at positions 1, 0, 1, 1, 2, 0, and 2, 1. Adding these together, we get a total of 7 square submatrices. This example demonstrates how we count both small and larger squares to arrive at the final total. In the second example, the matrix is slightly larger, with dimensions 3 by 4. The output here is 15. This includes 10 single-cell squares, where each individual one contributes a 1x1 square submatrix. Additionally, there are 4 larger 2x2 submatrices, each formed by groups of 4 adjacent ones. Finally, there is one 3x3 square submatrix in the top right corner, covering all the ones from 0, 1, 2, 2, 3. Summing up, we have 10 small squares, 4 medium squares, and 1 large square, giving a total of 15. This example highlights how multiple sizes of square submatrices can coexist within the same matrix. Now, in the third example, the matrix contains only zeros. Since there are no ones in the grid, it is impossible to form any square submatrices with all ones. As a result, the output is simply 0. This illustrates that when a matrix is entirely filled with zeros, there are no valid submatrices to count. Finally, let's look at the constraints and edge cases. The matrix can have up to 300 rows and columns, meaning it can contain up to 90,000 elements. This requires our solution to be efficient, ideally operating in O(m*(n) time. Some edge cases to consider include the smallest inputs, such as a single-cell matrix with either a 1 or a 0, and matrices with only 1 row or 1 column. For instance, a row filled with ones or a column with scattered ones can still form square submatrices. Another important case is when the entire matrix is filled with zeros, which results in an output of 0. For large inputs, such as a 300 by 300 grid filled entirely with ones or alternating ones and zeros, the solution must scale efficiently to handle the computation. These cases help ensure our solution works across a wide range of scenarios. To start, the brute force approach relies on a simple but computationally expensive idea. The intuition is straightforward. We iterate through all possible submatrices in the given binary matrix and check if each is a valid square submatrix containing only ones. The process involves identifying the top left corner of potential submatrices, then expanding their size step by step until we either encounter a 0 or exceed the matrix boundaries. For every valid square submatrix we find, we increment our count. While this method is easy to understand and implement, the trade-off is its inefficiency. The time complexity is O(m²(n²), as we are essentially evaluating all possible submatrices, and for each one, performing additional validations. The space complexity, however, is O(1), since it does not require any extra memory. Ultimately, the brute force approach is not suitable for large matrices due to its significant computational cost, making it impractical for real-world applications or competitive programming. Now, moving to an optimized solution, the dynamic programming approach leverages a key observation about the structure of square submatrices. Specifically, if a square submatrix of size kxk ends at a given cell, then there must also be a smaller square submatrix of size k1x(k1) ending at its top left diagonal neighbor. This observation allows us to build a solution incrementally by using a DP table. The size of the largest square submatrix ending at any cell depends on the minimum size of squares ending at its top left and top left diagonal neighbors, provided the cell itself contains a 1. Using the recurrence relation dp I(j) equals 1 plus min dp I1 j dp I j1 dp I1 j1, we can calculate the size of the largest square submatrix ending at each cell. The total count of all square submatrices is then obtained by summing up all the values in the dp table. To implement this, we initialize a dp table with the same dimensions as the matrix, populated according to the recurrence relation, and finally sum up the entries. This approach reduces the time complexity to O(m*n), as each cell is processed only once, and the space complexity is O(m*n) for the dp table, or O(n) if we optimize for in-place computation. The dynamic programming approach provides a significant improvement over brute force in terms of efficiency, making it feasible for larger matrices. However, it does come with the trade-off of requiring additional memory for the dp table. This trade-off is mitigated by the possibility of optimizing the space usage to O(n) if we compute results in place. Overall, we chose the dynamic programming approach because it strikes the right balance between efficiency and simplicity. The brute force approach, while easy to understand, is computationally prohibitive for larger inputs and fails to utilize the problem's underlying structure. On the other hand, the DP approach efficiently reduces the time complexity to O(m*n) and provides a scalable solution. Additionally, the recurrence relation used in the DP approach is intuitive, making the implementation straightforward. Alternative methods, such as using prefix sums or Fenwick trees, were considered but deemed unnecessarily complex without offering meaningful performance gains. Therefore, dynamic programming emerged as the most practical strategy, being both efficient and adaptable to optimization. In conclusion, the dynamic programming approach is the ideal solution for this problem. It balances efficiency with simplicity, making it suitable for both competitive programming and real-world scenarios. By leveraging the recurrence relation, we achieve a significant reduction in time complexity compared to brute force, while the space usage can be optimized for larger inputs. This approach not only handles the problem's constraints effectively but also scales well with the size of the input matrix. Overall, the choice of dynamic programming ensures a robust and elegant solution to counting square submatrices with all ones. To solve this problem, we need to calculate the total number of square submatrices within a given binary matrix that are entirely filled with ones. The matrix itself is composed of zeros and ones, and we're interested in identifying squares of any size, whether they are 1 by 1, 2 by 2, or larger, as long as they are completely filled with ones. One straightforward way to approach this is through a brute force method. In this approach, we initialize a counter to keep track of the number of valid squares. Then, we iterate through the matrix to identify all possible top left corners of potential square submatrices. From each top left corner, we try to expand the submatrix incrementally to form larger squares, checking at each step whether the current square is valid by ensuring that all cells within it are ones. This process continues until we've examined all possible squares for each top left corner, and in the end, the total count gives us our answer. Once we have identified a top left corner of a potential square, the next step is to determine if the square is valid as we expand its size. To do this, we calculate the lower right boundary of the square based on its size k. For example, if the square has a size of k, its lower right boundary will be at I plus k1, j plus k1. We then verify that every cell within this boundary contains a 1. If any cell is found to be 0, we stop expanding the square from this particular top left corner. However, if all cells within the square are ones, we increment our counter by 1 to include this valid square. This process is repeated for all possible square sizes k and for all top left corners within the matrix. Finally, after evaluating every possible square, we return the total count of valid submatrices. The brute force approach, while straightforward, has some inefficiencies. Since we are validating every possible square by checking all of its cells, this can lead to a significant amount of redundant calculations, especially for larger matrices. For example, when validating a 3x3 square, we recheck the cells that were already validated for the 2x2 and 1x1 squares within it. This redundancy makes the brute force approach computationally expensive, with a time complexity of O, m n m n caret 3. In terms of edge cases, we should consider scenarios like a matrix filled entirely with zeros, where the count will be 0, or a matrix filled entirely with ones, where the count will include all possible squares, calculated as the sum of squares up to the smaller dimension of the matrix. While the brute force method uses no additional data structures beyond the input matrix and a single counter variable, it is clear that there is room for optimization. By applying dynamic programming, we can avoid this redundancy and significantly improve efficiency. The inefficiency of the brute force approach stems from its high computational cost. With a time complexity of O, m n m caret 3, we iterate through every cell of the matrix and check all possible square sizes originating from that cell. This becomes infeasible for large matrices due to the excessive number of checks required. However, the space complexity of this approach is O(1), since we do not use any additional data structures other than the input matrix and a counter variable. To better understand how the brute force approach works, let's go through an example. Consider a matrix filled entirely with ones. Starting from the top left corner, 0, 0, we first validate a 1x1 square, then expand to a 2x2 square, and finally to a 3x3 square, incrementing the count for each valid square. We then move to the next top left corner, such as 0, 1, or 0, 2, and repeat the process. For the given example matrix, which is a 3x3 grid filled entirely with ones, the total count of valid square submatrices is 14. This includes the 9 individual 1x1 squares, 4 larger 2x2 squares, and 1 full 3x3 square. While this example demonstrates the correctness of the brute force approach, it also highlights its inefficiency, as we perform repetitive checks for overlapping cells in larger squares. This inefficiency motivates the need for optimization through dynamic programming, which we will explore in the next section. This implementation solves the problem by using a dynamic programming approach. The main idea is to calculate the size of the largest square submatrix ending at each cell, I, j, and sum up these sizes. The function begins by determining the dimensions of the input binary matrix using m and n. A variable total underscore squares is initialized to 0 to keep track of the total count of square submatrices. The algorithm iterates through each cell in the matrix. If the current cell has a value of 1, indicating it's part of a potential square, it calculates the largest square submatrix ending at that cell. For cells in the first row or first column, the largest square is simply 1x1, since there are no cells above or to the left. For other cells, it computes the size of the square at I, j, as the minimum of the values of the top, left, and top left diagonal neighbors plus 1. This ensures that only fully filled squares are counted. After calculating the size of the square at I, j, its value is added to total underscore squares. By the end of the nested loops, total underscore squares contains the total count of all square submatrices with all ones. The time complexity of this solution is O, m n, as every cell is processed once, and the space complexity is O(1), additional space beyond the input matrix. This makes it efficient for large matrices while modifying the matrix in place to save space. This is the Java implementation of the LeetCode problem number 1277, count square submatrices with all ones. The logic mirrors the Python implementation, leveraging a dynamic programming approach. Java-specific differences include type declarations, use of the math.min method for minimum calculation, and standard Java class structure. The solution iterates through the matrix, updating each cell to represent the size of the largest square submatrix ending at that position. The final count is accumulated during this process, ensuring an efficient O, m n, time complexity. To begin, we start with a small 2x2 matrix where all values are ones. The goal is to count all square submatrices filled entirely with ones. First, we initialize the dimensions of the matrix, m equals 2 and n equals 2, along with total underscore squares equals 0 to keep track of the count. As we iterate through the matrix, at position 0, 0, we find the value is 1. Since this cell is in the first row and first column, it can only form a 1x1 square, so we increment total underscore squares to 1. Next, at 0, 1, the value is also 1. Being in the first row, it represents another 1 by 1 square, so we increment total underscore squares to 2. Moving to 1, 0, this cell is in the first column and its value is 1, so it also forms a 1 by 1 square, bringing total underscore squares to 3. Finally, at 1, 1, the value is 1. Here, we calculate the size of the largest square ending at this position by taking the minimum value among its top, left, and top left diagonal neighbors, and adding 1. This gives us min 1, 1, 1, plus 1 equals 2, indicating a 2 by 2 square. Adding this to the count, we now have total underscore squares equals 5. After processing the entire matrix, its state is updated to reflect the sizes of the largest squares ending at each position. The final matrix becomes 1, 1, 1, 2, where the bottom right corner indicates the presence of a 2 by 2 square. The total number of square submatrices is 5. Now, let's consider a new example with a 3 by 3 matrix that includes a mix of zeros and ones. This input matrix is 0, 1, 1, 1, 1, 1, 0, 1, 1. The goal remains the same, to count all square submatrices filled with ones. In this 3 by 3 matrix, we initialize m equals 3, n equals 3, and total underscore squares equals 0. Starting the iteration, at 0, 0, the value is 0, so we skip it. At 0, 1, the value is 1. Since this is in the first row, it forms a 1 by 1 square, so we increment total underscore squares to 1. Similarly, at 0, 2, the value is 1, which also represents a 1 by 1 square, increasing the count to 2. At 1, 0, the value is 1. Being in the first column, it forms another 1 by 1 square, making the count 3. At 1, 1, the value is 1. To compute the largest square here, we take the minimum of its top, left, and top left diagonal neighbors, and add 1. This gives min 1, 1, 0, plus 1 equals 1, so we increment total underscore squares to 4. At 1, 2, the value is 1. Similarly, the largest square is computed as min 1, 1, 1, plus 1 equals 2, indicating a 2 by 2 square. Adding this, the count becomes 6. At 2, 1, the value is 1, and the computation gives min 1, 0, 1, plus 1 equals 1, so we update the total to 7. Finally, at 2, 2, the value is 1, and the calculation gives min 2, 1, 1, plus 1 equals 2, adding 2 more to the total, resulting in total underscore squares equals 9. After updating the matrix to reflect the sizes of the largest squares, the final state becomes 0, 1, 1, 1, 1, 2, 0, 1, 2. The bottom right corner shows a 2 by 2 square, and the total number of square submatrices filled with ones is 9. Now, let's analyze a simpler case, a 2 by 2 matrix where all values are zeros. The input matrix is 0, 0, 0, 0. In this matrix, we initialize m equals 2, n equals 2, and total underscore squares equals 0. As we iterate through each cell, all values are zeros, so no squares are counted. The matrix remains unchanged, as 0, 0, 0, 0. Since there are no square submatrices filled with ones, the total count is 0. To understand the time complexity of the solution, let's break it down step by step. The algorithm processes the input matrix using 2 nested loops. The outer loop iterates over the rows, and since there are m rows, this loop runs m times. Similarly, the inner loop iterates over the columns for each row. Since there are n columns, this loop runs n times for each iteration of the outer loop. This gives us a total of m*n iterations. For each cell in these iterations, the algorithm performs a constant amount of work. Specifically, it checks whether the value in the cell is 1, and then updates the cell value based on the size of the largest square submatrix ending at that cell. This involves at most 3 operations: comparing neighboring cells, performing an addition, and assigning the result back to the cell. Because each operation takes constant time and every cell is processed once, the overall time complexity of this solution is O(m*n). Now, considering the space complexity of the solution, the algorithm uses the input matrix itself to store intermediate results. This means the size of the input matrix remains unchanged, and no additional data structures are created to hold extra information. For each cell, the algorithm calculates and updates the size of the largest square submatrix ending at that cell directly within the matrix. Additionally, the only auxiliary space used is for a few integer variables, such as those for the matrix dimensions, counters for the loops, and the total count of squares. These variables require constant space, which is O(1). Therefore, the space complexity of the algorithm is O(1), as it operates entirely in place without allocating any additional memory. Let's compare this optimized approach with the brute force method to understand the improvement. The brute force approach involves iterating over all possible submatrices of the input matrix. Since the number of submatrices in an MXN matrix grows quadratically, this results in O (open parenthesis m times n close parenthesis squared) submatrices. For each submatrix, the algorithm would then need to verify whether it forms a square of ones, which takes O k squared time for a submatrix of size kxk. In the worst case, this leads to a time complexity of O (open parenthesis m times n close parenthesis cubed). On the other hand, the optimized approach uses dynamic programming to calculate the size of the largest square ending at each cell in O(1) time. By eliminating the need to check all possible submatrices explicitly, the time complexity is reduced to O(m*n). Furthermore, while the brute force method requires extra memory to track submatrices, the optimized solution achieves a space complexity of O(1) by modifying the input matrix directly. The time complexity, O(m*n), holds true across all cases, whether best, average, or worst. This is because every cell in the matrix must be processed exactly once, regardless of the values within the matrix. In the best-case scenario, where the matrix contains only zeros, the algorithm still iterates over all cells, but no additional calculations beyond the initial checks are needed. In the worst-case scenario, where the matrix is filled entirely with ones, the algorithm performs the maximum possible computations, determining the size of the largest square at each cell. However, even in this scenario, the overall time complexity remains O(m*n), because the number of operations is proportional to the number of cells. Mathematically, the total number of operations is the product of the number of cells, m*n, and the constant time required to process each cell, resulting in O(m*n). As for space complexity, since no additional memory is allocated beyond the input matrix, and auxiliary variables require only constant space, it stays at O(1). One of the most common mistakes when solving this problem is assuming that all submatrices are square by default. It's easy to forget that just because you're iterating over submatrices, it doesn't guarantee their dimensions are equal. To avoid this, you need to explicitly check that the height and width of the submatrix match. Another frequent error is implementing a brute force approach that checks every possible submatrix for ones. While this might seem straightforward, it becomes computationally expensive, with a time complexity of O(n to the power of 4, in the worst case for larger matrices. Instead, using dynamic programming or cumulative sums can significantly reduce redundant calculations, making your solution more efficient. Additionally, edge cases are often overlooked. For example, you might encounter matrices with only one row or column, or even matrices entirely filled with zeros. Testing thoroughly with these cases can prevent unexpected failures. Lastly, it's important to properly handle the binary matrix constraint. If your input contains values other than 0 or 1, your solution might behave incorrectly. Always validate that the input adheres to this constraint before proceeding with your logic. Another potential pitfall is the improper initialization of the dynamic programming table. When using a DP approach, forgetting to handle the first row or column can lead to incorrect results, especially since accessing out-of-bound indices can crash your program. Make sure to explicitly manage these base cases to ensure your solution is robust. Now, for interviews, there are a few key patterns to keep in mind. Many variations of this problem involve computing submatrices with specific properties, such as finding the maximum size, sums, or all ones, so mastering dynamic programming and prefix sums is crucial. Additionally, optimizing nested loops using memoization or pre-computed data structures is something interviewers often look for. While brute force solutions can be a good starting point, interviewers typically expect you to optimize to at least O(m*n) for larger matrices. Be prepared to discuss the trade-offs between time and space complexity, especially when comparing dynamic programming to prefix sums. When debugging, it's helpful to use small, simple examples that you can trace by hand. This not only helps you catch errors but also demonstrates to your interviewer that you're thorough and methodical. Don't forget to clearly explain how you handle edge cases, as this shows a deep understanding of the problem. If you want to deepen your understanding of this problem, studying related problems can be incredibly helpful. For example, LeetCode 221, Maximal Square, focuses on finding the largest square of ones in a binary matrix. This problem is highly similar and also relies heavily on dynamic programming techniques. Another related problem is LeetCode 85, Maximal Rectangle, which is slightly more complex because it requires finding the largest rectangle of ones rather than a square. For those interested in optimizing submatrix calculations, LeetCode 304, RangeSum Query 2D Immutable, introduces the concept of efficiently computing sums within a 2D submatrix using prefix sums. Finally, LeetCode 363, MaxSum of Rectangle no larger than k, is a more advanced variation that involves additional constraints on the sum of submatrices. Exploring these problems will not only strengthen your problem-solving skills but also prepare you for a wide range of variations that could come up in interviews. When tackling this problem, it's important to understand the trade-offs between different approaches. Starting with the brute force approach, it's the simplest to implement and can help you quickly validate the problem requirements. However, it comes with a significant downside: its time complexity is n to the power of 4, making it impractical for larger matrices. This is why brute force is usually only suitable for small inputs or as a brainstorming tool. Dynamic programming, on the other hand, is a more efficient approach, reducing the time complexity to m*n. Although it requires additional space to store the DP table, it's well suited for larger input sizes and is a technique commonly tested in interviews. Finally, the prefix sum approach offers even more efficiency for specific variations, such as those involving some calculations. While it's more complex to implement, it allows for fast range queries, making it a valuable tool when additional constraints or optimizations are needed. Understanding when to use each approach and the trade-offs involved will help you adapt your solution to different scenarios and perform well in both coding challenges and interviews. Great job! Today, we solved the problem count square submatrices with all ones using a dynamic programming approach. We discussed the time and space complexities, and key takeaways like the power of recurrence relations and optimization techniques. Thanks for watching, and keep practicing to sharpen your problem-solving skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!